Another vital element of programs are conditional or control statements, if and if else. Conditional statements allow us to use code branching. They are irreplaceable in situations when we have to execute a specific operation depending on a specific condition. In its simplest form, a conditional expression looks like this. It consists of a condition and a block of statements to be executed in a situation when the specific condition is fulfilled, that is, assumes the true value. Conditions are created using comparison and logical operators. We can see the basic operators on the slide. Conditional expressions may assume either a true or false value. You can see the basic variant of the if construction in the example. First, a random value is assigned to the los constant, and then the code using the modulo operator checks whether the random value is even or not. As we can see on the right, the random value in the example is 29. It's not an even value, so no information appears on the screen. This is because in our example we didn't specify what should happen if the condition isn't fulfilled. The foundation library is imported only so that we could use the arc4randomUniform function that returns a random value. In order to handle scenarios for even and odd numbers, we have to use a slightly more complex variant of an if-else conditional instruction. If the condition of the if expression is fulfilled, the instructions from the first block of brackets will be executed. Otherwise, the instructions from the else block will be executed. Our corrected example already handles the situation where the random value is odd. What should we do then in a situation when we want to check more conditions? The last variant of the conditional statement comes in handy here. With it, we can specify other conditions to be fulfilled so that the specific code blocks are executed, as well as what should happen if these conditions assume the false value. For example, we can check whether a random odd number is also divisible by 3. For this purpose, we use another if-else construction which, based on the modulo 3 operation, checks whether the number can be divided by 3 without a remainder or not. Of course, conditional instructions can be nested. The example of the code visible on the slide is very similar to the one presented before, but in this case, we use the if-else construction placed and nested in another if-else construction. Another method of grouping statements, which have to be executed depending on whether the specific condition is fulfilled, is the switch case construction. Switch is based on a control expression or a value which is then compared to the model in case clauses. In the example, we can see a code implemented using the switch case expression, which checks whether the given character is a vowel or a consonant. In this case, the control statement is the value of the character constant, and based on it, the proper print-in statement displaying the relevant message on the screen is executed. As opposed to other languages, for instance C or Objective-C, in Swift, there is no need to add a break statement at the end of each case block. This is because in Swift, after the first fulfilled condition is found, the others are not checked automatically as in C or Objective-C. There is nothing to prevent us from implementing similar switch case behaviors using Swift. To do so, We just have to use the fall-through statement. This is illustrated by the following example. For input number 5, the first case condition is fulfilled. So, to the initial value of the message variable, we add a message that informs us that we're dealing with a prime number. Then, the code from the default block is executed, and the information that our number is an integer is added. If the same code is executed for the initial value of 10, the end message only informs us that our number is an integer. As we've already seen in the previous examples, the switch case construction in Swift works not only on numerical values, as it is the case in many other languages, but also on any type of values. A very interesting option is to use the switch construction where the control statement is an object. The example you can see on the screen shows us how to handle potentially any event using a single code fragment, regardless of the object they were sent by. The example comes from a presentation at the Worldwide Developer Conference. As opposed to other programming languages, switch case in Swift has to take all the possible values of a control expression into account. If this isn't the case, the compiler will generate the error, switch must be exhaustive, consider a default clause, as shown in the example. As the message suggests, in such cases, it's good to use the default clause. A function is a code fragment that performs certain operations and which has been given a name. Each function is characterized by the following elements. It has its own name, which clearly specifies what the given function performs, or at least it should. It has 0 or more input parameters, and optionally, it returns a value or the data that is the result of its operation. We declare functions in Swift using the func keyword. The simplest variant of a function is a function that assumes no arguments and returns no values. In the example, we see a very simple display date function which displays the current date and time on the screen. In this case, in order to gain access to the NSDate class, at the beginning of the code, we have to import the foundation library. In the case of functions, there is often a need to pass parameters and arguments to them, since they are vital for their correct operation. We specify function parameters in a very similar way as the declarations of constants and variables. Specifically, we provide the parameter name ended with a colon in brackets. As we remember, it means is of type. Next, we enter the argument type. If we want to pass more than one value to our function, we separate the subsequent parameters with a comma. When calling the sample welcome function, we pass the name as a parameter. If we pass the name Peter as a parameter, as a result of the operation, we'll get the text, "Welcome to the world of Swift, Peter," displayed on the screen. When declaring the function arguments, we can also specify their values or default values. To do this, we enter the equal sign and its default value after the parameter data type. In the case of our function, the default value can be, for instance, stranger. After introducing the relevant change, our function would look as shown on the slide. Now, if we don't enter any parameter, we'll get the message, "Welcome to the world of Swift, stranger." An important issue we have to remember about is that if, after calling the function, we declare arguments with default values, we'll have to provide the name of the parameter whose value we want to pass. It can be seen well in the next example. we see that if we forget to provide the argument name, the compiler will generate an error, missing argument label. So far, all our functions performed a certain operation, but didn't return any value. Often, after having finished its operation, we need the function to return the value to the main program that called it. It can be a result of calculations or just a completion status that informs whether the action was completed successfully or not. In other words, whether there was an error. If we want our function to return a value, we have to modify its declarations a bit. To do so, we should specify the type of the returned value. This type is specified using a hyphen followed by a right angle bracket. I call it an arrow. After it, we have the name of the type of the returned value or the returned data. For example, the function that calculates the area of a triangle could look like this. We all remember the formula for the area of a triangle. It's 1 by 2 times a times h, where a is the length of the triangle's base and h is its height. Our function takes two parameters, base and height, and based on them, calculates and returns the area of the triangle. In this case, the calculation is simple enough to execute it and return the result in the same line without using any other local variables. For values where a equals 6 and h equals 3, the field of our triangle equals 9, and this is the value we see on the screen. Let's also pay attention to the triangle area variable. We didn't explicitly specify its type. There's no need to do that in Swift. The compiler knows exactly what type of data is returned by the function and can interpret our variable correctly. This is what it looks like when we return a single value. But what if we want to return several values at once? You can do it in Swift. To do so, after the arrow, we specify two types of data or more in brackets. We separate them from each other with commas. We can return as many values as we need from each function. A sample function that returns two values is the divide function from the example. It takes two arguments, integers, a dividend, and a divisor. It returns two integers, the total result from the division and the remainder. In the example, we also see how to call such a function and get two of the returned values. The approach would be analogous if the function returned three or more values. A curious thing is that if we return more than one value, we can name each one of them. On the slide, we can see the declaration syntax we use in such a situation. The example presented earlier, after slight modifications, could look as follows. It's good to notice that in the case of such an approach, we can assign the returned values to a single variable and refer to each element separately using the dot notation. Another element of the Swift language are closures. Actually, closure expressions are just unnamed functions. Objective-C programmers might see them as similar to blocks. However, before we focus on closures, let's look at one of the properties of functions which we haven't mentioned so far. What is interesting in the example we see? The possibility of assigning a function to a variable or a constant, and the possibility of passing a function as an argument to another function. Both examples are very simple. They were chosen on purpose to demonstrate this technique. It might not seem obvious at first how to use this option in practice. Let's imagine an application that draws diagrams of line functions f of x equals y. Such a function could assume any function of a single variable as an argument. For instance, y equals x squared or y equals sinus x. Let's look at the three functions from the example. Function w1 returns the value of a cosinus for the value passed as an argument. Function w2 returns the value of a sinus for the value passed as an argument. And the function draw draws a diagram of the function passed by the argument on the screen. First, we assign the function w1 to the variable fn and call our draw function. You can see the result of the operation in the diagram in the upper right-hand corner. Next, we assign the w2 value, that is, our sinus function, to a functional variable and call the draw function again. This time, the result of the operation is shown in the lower diagram. We see we can execute useful operations when writing more general functions and passing other functions as an argument to them. May I have your attention, please? The drawing function actually works in the playground environment. It visualizes the subsequent values of variables on the timeline. The actual iOS OS X function for drawing objects on the screen is a bit more complicated. Let's take a look at the next example. Here we can see the square function that calculates the value of the argument raised to the power of 2, that is, the argument squared. Then we declare a 5-element array and, using the map function, modify the values of all its elements. The introduced map function takes the function as an argument and executes it on each of the array elements. You can see the new values stored in the array on the right-hand side of the screen. The syntax of the closures helps us simplify this approach even more. Our square function, written as a closure, would look like this. Here we can see that the initial array values were modified correctly. We can think about closures as literals. For instance, one represents a number literal int, and hello world represents a string literal. Closures are also anonymous. They don't have names, which is how they differ from traditional functions defined using the keyword func. They may be used only in the way you can see in the example, by assigning them to the variable or passing as a parameter to another function. You might be wondering whether such a syntax may come in handy. Why shouldn't we simply create a traditional function using func and use it? Functions based on the closures syntax may be simplified a great deal as compared with classical functions. In the example, we can see that the square function and its 5 variants written using closures, from the most extensive from the syntax point of view, in other words, the one that initializes number array 1, to the most concise one, used in the case of declaring the number array 5. All the entries are unambiguous and based on the possibilities offered by the Swift language. If you pass a closure as a parameter, and it's the only thing you use it for, there is no need to use a local variable to store it there, a number array 1. It's analogical to passing an expression to the function. If the data types may be correctly interpreted or guessed by the computer, there is no need to explicitly specify them. In our example, the array elements are integer variables which, when multiplied by each other, will also be integer values, number array 2. If a closure expression is a single expression, we can omit the return statement, and then the expression value will be returned automatically, number array 2. Swift also provides the names of the function arguments automatically. $0 is the first argument, $1 is the second one, and so forth, number array 3. If the last function argument is a closure, it can be moved outside the brackets, which is particularly useful when our closures get more complex and take up several lines. Number array 4. If the function has no arguments, only a closure, we can skip the brackets entirely. Number array 5. If you haven't seen similar constructions in the programming before, the closures syntax may initially seem a bit overwhelming. With time, you'll surely become more confident both in reading the code written this way and writing your own closures. Since this isn't a course in object-oriented programming, we won't focus on its theoretical aspects, but on the implementation of classes in the Swift language. Remember that a class consists of fields, properties that store data, and methods. In Swift, we define a class using the class keyword, after which we specify the class name. Then, in curly brackets, we define the class's properties, its methods, and optionally, the initialization function. For instance, the class point that includes all the previously mentioned elements could look like this. It has two properties, the coordinates x and y, the shift method, and an initializer that sets the initial coordinates of the point to 0, 0. If you have already programmed in Objective-C, you'll be happy to hear that in Swift we don't need to create and import interface files, meaning header or H files. Inheriting in Swift looks similarly to other object-oriented programming languages. When declaring a new class, we specify the base class after a colon after the name of the child class. We declare class objects similarly to variables, starting from the keyword let or var. In the case of let, there is no need to specify the type if we initialize the value immediately. The situation is similar in the case of variables if we want to initialize them right after having declared them. If we don't do that, it's obvious that we have to specify the type of the variable after the colon. Also, we don't have to worry about memory management. Swift will take care of that for us. We can refer to particular properties or functions by using the dot notation. In the example, in the last line, we can see the statement that displays the width of our object, the shape. Now, let's look at a slightly more complex example. We'll start by creating a base class, figure, described by two properties, the height and the width. We create a new class called rectangle and inherit from it. Additionally, in this class, we declare the computed property, that is the area, and the isSquare function. It returns the value true if the rectangle is a square, that is, if its width equals its height, and false if it isn't. In this case, our property is a read-only property. It's good to remember that the calculated values aren't stored in the memory. The relevant value is calculated the moment we refer to the given value. Next, we create the object of our class, that is its shape, and define its height and width to 4. The next line displays the computed area, that is 16, and yet another line correctly tells us that our shape is a square. Note that if the method parameter has the same name as any of the class properties, we can refer to this class property using the self keyword. If we want to change any value of the base class in the subclass, we have to implement in it the init method, override init. In this case, it's necessary to call the init method of the base class. It has to be the first called method, in contrast to Objective-C, where we called the super init method at the end. For instance, the vehicle class and the car class that inherits from it might look like this. In the new init method, we change the number of car wheels to 4. We also add a new property, gear, which we'll use in a moment. We also have to use the override keyword if we want to change the behavior of the computed class properly. In Swift, we also have property observers at our disposal, thanks to which we can perform a specific action if the value of the property changes. It is done by using two methods, willSet and didSet. The willSet method is executed directly before the property value is changed. The didSet method, by contrast, directly after the change of the value. Let's return to our sample car class. Since our car has an automatic gearbox, the value of the gear will change depending on our speed. Naturally, we're simplifying this a bit for the purpose of the exercise. The gear change implementation was included in the didSet method. The moment the speed reaches a value in any of the specified ranges, the relevant gear is shifted.